Okay, today, thank you for coming to the second special topics lecture. I'm really excited that I was able to give the one Tuesday on compilers. It was a lot of fun, and I'm hoping this one will be similarly fun. One thing to note is I am very, very tired, so I got to reset the momentum. Okay, let's get this going. I cannot coast off the momentum of previous shows. All right. Program analysis. What is program analysis? Well, I talked to you about compilers, and compilers are pretty cool, but they're not as cool as they could be, because the thing about a compiler is like stodgy and dodgy and it has no fun. Okay, it doesn't go out on weekends, it doesn't party. Program analysis, by comparison, is hip, it's cool, it has more than 2 friends. Okay, so our metric for program analysis here is going to be first of all, we have to talk about what program analysis is. And then maybe we'll get into why it's cool, okay? So I have a few things for you, but let's get into it, shall we? I am wearing my shirt. Thank you for pointing that out. All right. I'll clean this up somehow. All right, let's not clean, please. Okay. Last time, nothing. But last time is like nothing. Forget everything that happened. I'm kidding. The last lecture is actually quite relevant to this one. Okay. The state of software. Well, before I can talk about programs, the things we want to analyze, I got to talk about programs, like software, like the real world. And I know, scary. We live at CMU. We're here in our academic bubble, but I come from the industry and I come with tidings from outside. Okay, so the state of software is long ago, long before you were born, on August 20th, 2011, entrepreneur and Silicon Valley venture capitalist Mark Andreessen, he published this article called "Software is Eating the World." And this was mostly focused on like economic and financial reasons, such as business-oriented reasons, I should say. Which is that at that time, software was really starting to take over. You started seeing all sorts of economic sectors being impacted by this ease of communication, this ease of access, ease of usage, because the internet, by the way, is pretty convenient, in case you weren't aware, okay? So among other things, like your ability to reach brand new audiences was unprecedented, right? So nearly a decade after this article, this is not a surprise to anyone here, okay? Like, we are very aware. Software has already eaten the world. Software has won. We are living in the cesspool of software, okay? We are in a post-software world. So the point I'm making to you is simply that Mark Andreessen, currently board director for Meta Platforms, bless his heart, he was right, okay? But now, what about software engineering, which I know some of you are interested in? Software engineering is currently, and very much is, a lucrative job with a lot of jobs available. Why? Because everybody needs software. It doesn't matter if you're a think tank, if you're a massage parlor, if you're a pet store, okay? You need software. You need a website. You have data. You have customers, which means that everybody, no matter where they work, needs software. Yeah. Well, you would have thought that would have happened already, but this demand is still so high, like, yeah. Yeah, I don't know. Anyways, so the point is that software has embedded itself into every aspect of our lives, and that's great news for you studying computer science, because it means that if you want to have a job, you're going to have a job, right? At least, well, that's what the class of 2023 thought too. But the point is that not every single software engineer in the world was educated at CMU. Not all of them have taken 15150. And that means that not all of them know about the importance of writing either, take your pick of correct code, safe code, good code, so on and so forth. Okay, the things that I've been wanting to teach you all semester. So we have a little bit of a problem here, because there are tens of millions of software engineers out there in the world. Okay, and one thing I've always said to you in this course is we're trying to produce as little code as possible. Why? Because every piece of code, every line of code we write has the possibility of a bug. There was that one time I literally said, like, oh yeah, if you write something too many times, you write it wrong, and then I wrote it wrong on the board. And then if you review the VOD, it's actually very funny. But what do you think we can say then about the overwhelming deluge of software that's being produced by these tens of millions of software engineers everywhere around the world? What do you think we can say about all of this code? Would anyone like to hazard a guess? Yeah.
It's shit.
It is so unbelievably horribly messy, and we're in the trenches right now. We are screwed. Okay? Unrestricted access to code writing, and it's on a level that's unprecedented, because guess what? You used to have to at least look at a Python tutorial for 20 minutes online to code. Now you can plug a prompt into ChatGPT and you can code. And guess how many of them are thinking about the correctness, the cleanliness, or the beauty of their code? Guess how many times ChatGPT is thinking about that? So we're in a spot where we're reaching more and more importance in terms of being able to make sure that our software is one of these three things. We want to make sure that we are producing good software. We're not in the business of writing code. We're in the business of writing correct code again. So what do we do about it? Well, what does it look like when you write a mistake in your code? Okay. For instance, it might look something like this. Maybe you made a typo. Maybe you meant to call fact recursively. And then how do I fix this? Well, I call it for real, right? Maybe when you make a mistake, you declare a variable and you forget to use it. Actually, this is I have a bone to pick with this one. This is a very really important one. What's happening here basically, I'm showing you treefold-L. I declared this left folded thing, and oop, I didn't use it. All right. SMLNJ does not natively give you a bug for this, but good compilers will. We replace it with left folded. But this is another classic mistake. You were just off somewhere else. You pushed it on your stack. You said, okay, I'm going to declare left folded, and then you were done, except that then you forgot about it. Very classic kind of mistake that you can make. Raise your hand if you made this one. Right? Yeah. So, or maybe you just have something as simple as a type error. You call fold R, and then what did you do? You didn't give back all of the arguments. Maybe you gave fold R, you didn't give fold R F, which you should have done, the combining function. And then fix for that was obviously just to add it back. But these kinds of things are errors. Programmers make errors all the time. Okay, I would say that the main thing that we got out of last lecture with compilers is, why do we improve over assembly language? Well, first, we can write code faster, and secondly, it'll tell us anything about the code that we're writing, right? So these simple mistakes happen all the time. And SMLNJ won't warn you about this one, but that's okay. It could theoretically. So we're lucky to work in a language where it'll warn you about most of them. If you misspell, it'll warn you. If you make a type error, it'll definitely warn you. All of you are very aware of that fact, right? But some languages do not have that privilege. Python in particular will literally warn you about none of them. Okay, I'm so serious about that. And so what I want to be able to say is, I want to be able to catch these errors at compile time. And if your language doesn't have a notion of compile time, like before it runs, basically. But before I run the program, before I stumble over it, I should be able to say, hey, something might actually come up when you execute your program. Because otherwise, what am I executing my program for? Okay, I'm just running over stalagmites with my eyes closed for no reason. And I always like telling this story when I'm motivating this kind of thing. But why do I want to catch errors statically? All right, here's the story for you. You are a machine learning engineer. Ah, horror. And you spent 6 months working. Oh, that TV's on. I just realized. You spent the last 6 months working on this large language model, and you're real proud of it, and you want to put it to the test. So you rename some stuff, you leave some comments, and then you're like, okay, looks good, LGTM. You push it, and then you go on a vacation to France after running it. Okay, and then while you're in France, you have a great time. You come back, and your model failed with name error. Name modelly is not defined. Did you mean model? This actually could happen. This actually does happen. Okay, you could be 200 compute hours in and then not know that your program has a simple typo that'll just mess your day up. SMLNJ knows though. Why? Because what it's doing is the compiler needs to know a lot of things prior to letting you run your code. It's a responsible parent that's not going to let you run into the playpen with the knife out. Okay, so the point is that this is the knife out. This is the bad thing. Okay, so let's try to do better than this, right? So what's my point here? Okay, programmers make mistakes. Wow, crazy. But there's a lot of programmers in the world. And these silly mistakes, if there's a 0.01% chance of it happening, guess how many times it's happening? A lot, okay? A lot of times. So we need to be able to make sure that our compilers, our tools, our programming languages are capable of making sure that these errors, and more advanced errors even, don't happen. Because the cost of doing so is really, really high. Remember Tony Hoare? His billion-dollar mistake. We're talking about this battle, this uphill slope where there are billions and billions of dollars resting on this, because that's just the scale we're talking about when it comes to the software, the amount of software being produced in the world. And it's not just a wanting to thing, it's a security thing. It's making sure that we can be safe about, or relatively assured that our society will continue to function. And the outlook is not looking good on that front. Okay. So how do we fix these mistakes? What do we do? Okay, why am I saying all this? How do we make sure that all of this software that exists is going to be okay? Well, software's eating the world. Let's bite back. There's a reason why this is called program analysis. we're going to talk about program analysis next. And I highly recommend this book. A coworker recommended it to me. I think it was pretty sobering in terms of the things I've been alleging to. Okay, let's bite back. Program analysis. What the hell is program analysis? Well, program analysis is the art, I'll say, of discovering unwanted behaviors in programs, usually by automated means. As humans, we do a kind of program analysis ourselves. Like, I see you use val. Actually, I don't know what to put here. I was going to say something about like style grading, but I don't actually care that much. But my point is basically, I can look at your code and be like, maybe you shouldn't have done that. Oh yeah, if you do this, who's ever done this? Don't do this. This is like things in SML you shouldn't know about, but it's the second to last lecture, so I'm allowed to spoil it. This is like a terrible primitive that you should instead use pattern matching for. My point being, okay, that program analysis is how we find these unwanted behaviors. And this might include a lot of things. It might impact the correctness of our code, the performance of our code, the security of our code, which is tied to correctness. But it's really any property that it's worth noting about a program, which are a lot potentially. And at its core, program analysis is the art of writing programs that analyze programs. I'm big into meta kind of stuff. I'm big into recursion. So to someone like me, this is like catnip. Okay, I love this kind of stuff. And usually comes in one of two flavors here. Okay, two special herbs and spices. One, we've got dynamic program analysis. Raise your hand if you've heard this term. Okay, that's fine. I was wondering. Dynamic program analysis means I'm going to figure out the properties of this program by running it. At runtime, I'm going to instrument it maybe and then discover something about it. So there's a technique called fuzzing, where basically you throw a bunch of random inputs at a program and you see if it like throws bad or if it doesn't meet some kind of specification. Profiling you might consider as well, which is literally just running your code and then measuring how long it takes. I might call that like a dynamic program analysis. It involves running the code, or even just running tests or writing tests that will run. Dynamic program analysis is pretty cool. It goes straight to the point. It actually evaluates presumably what the program does. But that's also not a great thing, because it means that the time it takes to run a dynamic program analysis is tied to how long it takes to run the program itself. If it takes a really long time, we might have to wait a really long time to evaluate it. Or if it loops forever or crashes, well, then we're going to do the same, right? So there are really good applications for this. And generally, when you're writing software, you want to have a mix of this and the next one I'm going to talk about. But we're going to focus less on this. This interests me, a PL nerd, less. Okay. And then this is where it's at. This is static program analysis, which is, as you could probably guess, trying to figure out properties of programs without ever running it. How could I do that? Well, if only there was some kind of funny, like tree-like form I could put a program into that I could then, evaluate to figure out the behavior of. Oh, wait, didn't we talk about that last lecture? Yes, we did. So programs are trees, right? Which means we can write simple recursive functions that just go down the tree and figure something out. Maybe they figure out, oh, you could have folded this constant. Maybe val x equals 1 plus 2. Maybe this could just be 3. But maybe it doesn't need to fix it for you. Maybe it might warn you in your IDE. That's a static program analysis. This will be our focus for today, and there's a couple of different reasons why this is important. One of them is sort of the domain I work in, static application security testing. That is static program analysis for the purpose of security. Scan your code to figure out whether or not you are vulnerable to some outside attacker, which is really, really important, okay, even though I won't talk about too much today. Also, something as basic as syntax highlighting. Taking something that might be an incomplete program and try to color it. I would call that a kind of program analysis, albeit one that's maybe a little less interesting. Or auto formatting. If you've run an auto formatter, it takes your code and it auto formats it. I don't think I need to explain that. That I would say is also kind of like analysis of what your program looks like, of what your program is. Or type checking even is the most fundamental kind of program analysis that you're very, very familiar with. A type checker just looks at a program and then figures out what all parts of it have the type of, if there are any such things, okay? I would call that a program analysis of itself, okay? So this is the mission, okay? This is where we want to go. But before I can talk about the technical details that go with this, there's one small, tiny, bite-sized, atomic issue in front of us. And that issue is the fact that program analysis is inherently impossible. How many of you have taken 15251? Then you probably know what I'm alleging to, which is that program analysis, there's this one nice little theorem in mathematical computability theory, which states all non-trivial semantic properties of programs are undecidable. And if you don't read Rice's theorem, okay, and by the way, this is like a real theorem. Like this will apply to everything. In English, what this means is this. You cannot answer definitively yes or no in a finite amount of time for literally any property of a program's behavior in general. You can't do it. It is impossible. Okay. And you might be thinking, Brandon, like, what do you mean? Well, okay, let me give you a concrete example. And this comes out of something called the halting problem. Raise your hand if you've heard of the halting problem. Yeah, okay. The halting problem is this. You cannot write a program to tell if a program loops forever or not, okay? And there's a really simple demonstration for why this ought to be impossible to determine. And it comes out of asking, what does this function return? Suppose, so we're going to do this by contradiction, all right? Suppose you had a function halts, and what this function does is it returns a bool if the function you give it halts, okay? On any input, I guess, maybe. Doesn't really matter, coding details. Anyways, what does this do? Well, okay, we got a function here that if halts is true on itself, then it loops. Otherwise, it returns unit. So let me do this by casework. Okay, we got case one here. We got case one. I don't know whether or not halts or not, right? But let's say that not halts. Well, if not halts and halts is true, this should be true, yes? Then I should loop. So if not halts, that implies it loops. And then case two is if not halts loops, well, then it means that halts should be false, right? It's not true that it halts. So this will evaluate to false, so we enter here. But if we enter here, that means that not halts returned a value, which means that it definitely halted. So it implies that it halts. What does this remind people of? Well, it does remind you of the halting problem. That's a tautology. But one thing I would go for also is if anyone's heard of the Epimenides paradox or the liar's paradox, okay? All Cretans are liars. This sentence is false. It should feel a lot like that because it basically is that, okay? My point is that we're going to find that we cannot have this program halts. Because if we did, we could construct this, and then we have a logical impossibility, which is that this function somehow both halts and doesn't halt, or it does neither. It's okay. Well, raising exception is possible, but that doesn't matter. Okay, raising exception is not halting. Do people understand what I'm getting at here? This is just a very simple explanation of the halting problem. The point is that paradox means bad, means we cannot solve it. We cannot write a program to do it in general for any program. Okay, it's not possible. And then it turns out because programs can do whatever they like, this will taint everything else that we would like to be able to do. Nothing else is safe. So therefore, Rice's theorem, if I ever want to figure out some kind of property of a program about its behavior, you're shit out of luck. That's exactly what it says. Okay, quotes and everything. All right, Rice was ahead of his time. Okay, so tiny, atomic, really small problem. Program analysis is impossible. So that sucks. Lecture over? Not quite. So lecture is only over if you're a quitter, basically. All right. Yeah, only 63 slides left. This only sucks if you're a quitter. All right, and we didn't raise quitters. So remember this idea I've kind of alleged to, which is either strengthening an implementation or weakening a specification when we want to implement a function. Basically, that means that either we can suck it up and then put more work into our implementation, or we can just lower our expectations. We are dealing with a mathematical impossibility here. So it's not a skill issue. Like we don't need to strengthen our implementation. Okay, that's not the problem here. The problem here is that our expectations are too high. So it is impossible to definitively answer yes or no for any property in a finite amount of time. Yes, that's true. But it's only true if you insist on being right all the time. This is the main contribution out of program analysis. Let's be wrong. Let's be wrong. Sometimes, not all the time. So we're facing an impossible problem, but let's just lower expectations. So compilers and program analysis are very different because I impressed upon you earlier the importance of a compiler. You have to be right. You must be right. You can never be wrong because if you do, doomsday. But program analysis, it's kind of like, oh yeah, you tell someone, oh yeah, you might have a vulnerability here, and they look at it and they're like, what do you mean? No, we don't. And then you're like, oh yeah, my bad, sorry. And then people still use them because it's the best we got. Okay. So a compiler can never be wrong, but program analysis is okay. We can throw up our hands, say, I don't know. We can also give an inaccurate answer or an incomplete answer. Those are all perfectly valid outcomes for program analysis, but we're going to see how well we can do given that. Okay, was there a question? Okay, I thought I saw a hand. Okay. A fun corollary of this I like is something called the full employment theorem. It's like a meta theorem. It's like a fun little social experiment. But it says there will always be jobs in either program analysis or compiler writing because we're talking about an impossible problem. It means that we can always make progress for any program analysis. Anything that we do, we can always do a little bit better if we just do a little bit more casework. Okay, let me demonstrate this to you. No one's stopping you from writing the halts program on a few examples. I just case val x equals 1. Okay, it returns sum of true. And if it's not, it means I don't know. Okay, or I don't care. Val x equals 2. Yeah, it halts. Val x equals 3. Yeah, it halts. Fun loop x equals loop x. And then I call loop. That one doesn't halt. I can look at it with my human eyes. And I say it doesn't halt at all. No one's stopping you from doing this for the next 60 years of your career. Okay, so full employment is always ensured. We can always add another case to our match, and that's okay. All right. So basically the point is that a team of monkeys at typewriters could eventually make a program analysis tool that's better than whatever exists currently. Okay. Which might be unsettling to you, but actually to me it's somehow motivational. Okay. I could be that monkey. Okay. It's me. Right. So let's try it. Okay. Okay. So we have an impossible task in front of us. We cannot do anything about the fact that it's impossible to solve, but we can stop whining and we can get to work because software is still eating the world. And the cost of failing is pretty high. We have a lot of consequences for us if we fail to do something about the deluge of software that's crashing into us at breakneck pace, okay? But program analysis, we're going to do our damnedest, all right? Let's get to work. So next up, let's do the impossible. Shut up and do the impossible. Someone's like, it's impossible. This compiler has a bug, except for the one time it did in lecture, okay? No, shut up. Do the impossible, all right? Let's talk about a specific example called type checking, okay? You're familiar with type checking at this point, and we're going to talk about it in the context of standard ML. Type checking always terminates, I'll tell you, okay? Even if, well, it should have been pretty fast for you, but it always terminates, and it always gives you a correct answer. If it gives you some type, you can trust that it has that type, and if it says it's ill-typed, you can trust something is messed up, okay? But let's talk about this function right here, this fun function that we introduced on the first day of class. Takes in 2 ints, gives us back an int. What is the remarkable thing about this function you think I'm going to talk about? What is the cool thing about div? Div 1? Div 0? Yeah, okay. Div 0. What happens if we divide by 0? Well, raise div. That's a pretty bad thing. But it means that SML will just let me go ahead and run a program that says this. It'll just be like, yeah, okay, boss, sounds good, and then run it. And isn't that exactly what I said we shouldn't do? We shouldn't have to be able to run into an error at runtime if we can avoid it, okay? So what if we could give div a more particular type, one that meant that we could never pass in 0 here, so that if our program ever passes 0 into div's second argument, we would get a type error. We would never run the program. That'd be pretty cool, right? That would cover one such use case. Okay, let's just focus on this for now. Let's try to do it. Well, okay. So what would we do? Well, okay, there are 2 properties that we would want to have for if I was able to give div this special type. Okay, one property is I want to be able to ascertain that type in a finite amount of time. What I mean by that is the type checker should not loop. If I want to do this for div, I should not have that my type checker ever loops, because if I wait around all day for my program to compile, I'm going to be sad. Okay, I don't want that. Okay, none of you want that. All right, that's a bad thing. 2 is, this is wordy, but it basically just says it's correct. If it says ill-typed, it should be if and only if either there's 0 or I did something else stupid that we know about, like I gave it something ill-typed. One of these 2 cases. We would like to see that both of these hold, okay? But actually, based on what I told you earlier, it is literally impossible to have both of these things at the same time. You cannot have your cake and eat it too. You cannot eat your cake and have it too, okay? Whether or not you say it the Kaczynski way or not, this is still not good, okay? None of you get that reference? Okay. So looping forever or being wrong, pick one, okay? Cope. So we're going to have to decide, because due to the halting problem, if I wanted to be completely correct, I would have to accept the fact that I would, or rather, I can't have both, okay? Or not both, rather, okay? I cannot both be finishing the finite amount of time and be correct. There we go. So what do we do about it? Turns out, actually, there are things that let us do this. They're called dependently typed languages, and they let us prevent things like this. Like, oh yeah, I want to make sure I never get 0 into div. I want to make sure that's a compile time error. The trade-off here is that these things might loop forever at type checking time. I'm going to call that a type A program analysis. Okay, I'm going to separate them into a couple, but we're going to say that a type A program analysis may loop forever, which is something you might be okay with. It depends on your sensibilities, but this is a type A program analysis. Dependently typed languages count. Okay, so the other way we could do it is we could get the first property but not the second. We could have it such that we are always correct, or sometimes, sorry, rather, we're sometimes wrong, but we always terminate. So that's going to be what we call a type B analysis, sometimes wrong. And I'll just, to make sure everyone's on the same page, I'm going to put in parentheses here, like it might loop forever, but when it gives us an answer, it's always right. And then a type B analysis is sometimes wrong, but it always terminates. I suppose you could have the worst of both worlds and have one that both may loop forever and is sometimes wrong, but let's focus on this for now. That's obviously not a good thing, okay? Let me give you an analogy for this, okay? You are in charge of security at an airport, okay? And you're aware that in the early 2000s, someone tried to set off a shoe bomb. In fact, they had plastic explosives concealed in their shoes during a flight from France to Florida. Okay, they snuck it past security and then they tried to light a match on it on the plane, and then they got tackled, and then thank God nothing happened. Okay, but you're very aware that this shoe bomber happened, and you somehow, for some reason, you are interested in making sure that shoe bombs do not happen. Okay, for some reason. How do we do that, given that we can't scan the shoes? Like when they walk through the metal detector, you might not find out. Well, you don't have a good way of telling whether or not anyone a priori has explosives in their shoes. So how do you do this? This is why everyone needs to take off their shoes in the airport. Okay, this is exactly how type B program analyses work. Okay, the point is that if you can't know exactly whether or not who has explosives in their shoes, it's actually really easy to get an approximate answer. Assume everyone has explosives in their shoes. Make everyone go through the metal detector. So scan everyone's shoes. Now you're good. And this is literally how that works. So for this broader goal I had of typing div so that we know whether or not div gets 0, let me propose to you a method for how we might do this. If we don't mind being wrong, fun contains unsafe div given a program simply contains if that program contains the literal string div. So we will accept programs like val x equals 1 plus 1, but we will reject programs like val y equals 1 div 1. Like, yeah, if you don't mind being wrong sometimes. I mean, we're guaranteed to terminate, right? Does this loop? No, it just checks the string. Sure, I don't see the problem. So type B. And also, they would also complain if you did this, of course. But, you can't win everything, all right? What can you do? Deal with it, all right? We have to take extreme measures when we're solving a literally unsolvable problem, okay? We're trying our best. So which of these is more preferred? Do I want to be able to loop forever when I type check my program, or do I want to reject every single program that has div in it? Turns out the answer is I want literally none of these. I would prefer none of these. So with more sophisticated techniques, I might be able to reject better programs than this. Like I could check whether or not I had a literal call to div. But the point is that I will never be able to get every use case. I will never be able to actually say yes or no on every single proper div call to 0 without looping forever potentially. Okay, yeah. Yeah, but what happens if then I give you this? One div, an arbitrary function f call. Now, what if f loops forever? But it's not provable that loops forever. Have you ever heard of something called the Collatz conjecture? Yeah, the Collatz conjecture says that if x is even, then do 3x plus 1. Else, if it's odd, do x over 2. By do I mean I'm doing a recursive call that will make this x equal to that. Okay. Okay. My point being that we don't know whether or not this terminates. Shut up. We don't know whether or not this terminates. It is currently a $1 million open problem whether or not this terminates. It's not. Okay. It's not 1 million. But the point is that we don't know. So what if I put it here and I did something to it? I added 1 to it. I made it sometimes 0, right? So yes, we can find things like this. I agree with you. We could do that. And we could not do the stupid thing where we reject a string of div. That's a little better, but we can't do it the general case. Yeah. The programs are trees, which means they induce a tree structure, but the tree doesn't say anything about how it runs. It says something about how it might run. What I mean by that is like, if I gave you a general program, okay, and I didn't know anything about it, and I showed you this code, if x is even, else blah, you have no idea of telling me whether or not we might enter this case or this case. Without running the program, you have no way of knowing which branch is taken. But the tree tells you, oh, you might go here, you might go here, but it doesn't tell you which one. Same idea with the control flow graph from Tuesday. It tells you the possibilities of where you may go, but you have no idea which path you're going to take, if at all, right? So that's the problem here, okay? So the point being basically that I don't care. I simply do not care. We're just going to not try to type div at one where we can reject this division by zero case. So I'm going to actually call that a type C analysis. A type C analysis is where you wimp out. You just decide this problem is not worth solving, and you decide to solve an easier problem. This is what type checking is. Type checking, we said, I want to be able to catch one div 0. And then we said, actually, that's too hard. Let's just not catch one div 0. Okay, let's just do ints. And that actually turns out to be tractable. It turns out to be solvable. Blah, 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 blah. So the question here is basically like, does this program divide by 0? We decided I don't care, because either I have to accept looping forever, or I have to accept looping forever, or I have to accept rejecting a bunch of programs that are valid. But what about a different problem, which is a different question, which is, does this program divide by a non-integer? Turns out that one's fine. We can solve that one. It's a type C. It's a wimp out situation. Like, we can solve that one in finite time, and we can always be right about it. But it's only because people have put decades of research into figuring out which problems can be solved by a type checker. Okay, it happens to be that us living decades and decades after assembly, we can be sure that our programs will not loop when they type check. Okay. And the reason for this in kind of a conceptual way is that non-integer, that's approximative, right? That's pretty broad. It could be 0, could be 1, could be 2, blah, blah, blah. But 0 is specific. As soon as you start asking any question about a specific value in a program, you're hosed. In general, you're hosed. Because how do I know without running the program, right? The Collette's conjecture. Does the Collette's conjecture ever reach the number, blah, blah, blah? We don't know. We don't know. We can't know, okay? In general, that is. Okay, are people following me on this? Thumbs up, thumbs down, thumbs sideways. Give me a temperature check. Okay. I try not to give away who I'm looking at. I like to do it. Yeah. I don't want you to feel bad about it. Okay, let's recap. All right, let's recap. So I want to be able to answer specific questions about programs. It's this security thing. It's a making sure our programs work thing, which is impossible. So I have to give up one of these things. I need to either give up guaranteed termination, give up perfect accuracy, or give up the problem I wanted to solve in the first place. And type A, type B, and type C analyses will correspond to each of those things. And let me put here in parentheses, solve a different problem. Okay. Specific examples, as we saw, is dependent type checking can loop forever. So it's type A. Rejecting literally all programs that have div in it is a type B, because we can reject a valid program. And then regular type checking is type C. Give up and then we don't care about the dividing by 0. Okay. And it turns out now, so I've talked to you a little bit about the theory of program analysis. We're going to talk about it in practice, because it turns out that people are not super happy when you put things into their build processes and their CI and their programs that run on their pull requests when they loop forever. People generally do not like that. So type A is right out. We cannot have type A in practice usually. Okay, we do not want to loop forever. So generally, we're interested in either sometimes accepting the probability of being wrong, or just solving a different problem, an easier problem. Okay, these are the ones we're going to focus on for the rest of the lecture. Okay, and I already said this thing about how decades of work by type theorists, blah, 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 blah. Okay. But for some things, so type checking still has this opportunity to be type C, but for some problems oh, are you vulnerable to SQL injection? Is this code reachable by a caller? Does this program exhibit unsafe behavior? We have no guarantees. We don't know, okay? So we have to be in type B for these ones. And these are the interesting ones. So let's try being wrong, okay? Some of us don't need to try, okay? I don't need to try, but let's be wrong, all right? Data flow analysis. This one is conceptually difficult. I want you to get the idea as usual. And unless you take compilers, you will not need to actually know the precise coding details of how it works. Okay. Here's how it goes. This is a very, very classic technique. This is used in every single compiler, every single program analysis. It's our bread and butter for how we get facts about a program. Data flow analysis is a type B analysis. It will always terminate if you set it up right. But sometimes it will like over approximate or under approximate or make assumptions that will not always be true because it needs to make assumptions. It doesn't know. Okay. But before I can define it to you, I got to give you an analogy. Okay. And the analogy is this. So the analogy is not val x equals string high div 0. All right. I have a question. I have a question about programs, and I have a certain number of answers. In fact, I have n answers. Suppose I have finitely many of them. And suppose they're all different, okay? I'm being very, very abstract here, but like your question might be, oh, does this program type check? And your answers might be yes and no. Or it might be yes, and it might be no because of a type error at line 2. Or it might be no because of a type error at line 3, so on and so forth. My point being that there are a finite number of answers. Now, the problem with program analysis is that in general, these questions, if they're about program behavior, a program can go to literally any state it likes. If what a program does at runtime is completely unbounded. So for instance, if I'm asking a question like, how much memory has this program taken up at this point in time? We might start here, and then we go here, and then we go here, and then we go here, and then we just jump all around. And we might do that infinitely long. We might keep doing that because our program might not terminate, okay? Memory consumption is a good example. So jumping all around like this, we're guaranteed that we might loop forever. But what if we refactor the problem? What if I enforce a guarantee the same way that we enforce a guarantee on the associative function to reduce? We enforce a guarantee so that we can get nice things out of it. What if every single step of my program, every step of my analysis, I always have to go right? If I put my answers, there's a way of putting my answers on a number line such that I always go right no matter what, or I stay where I am. Well, do you believe me? Does it make sense to say, if I always go right or stay where I am, I can guarantee terminate. I can guarantee termination. Because as soon as I stop being able to move, I know I'm done. That's my answer. But if I always go right, eventually I'll hit the end. Does this abstractly make sense to everyone? Okay. So let's think about it. This is the idea of what's called a monotonic function. Oh, whoops. This is what I just said. This is what's called a monotonic function. A monotonic function always increases by some metric. And I'm not going to define that for you because I don't care. Okay, but the point is that it always increases, quotation marks, and it always has a maximal upper limit, a point where it can no longer grow. For data flow analysis, what we're going to do is we're just going to spam that function. We're going to spam it and spam it and spam it and keep doing it until eventually it stops. And then we know we have our answer. Yeah. I'm abstracting over every possible thing you could have asked. But like, let's suppose the question is, how many calls to F? Okay, we can have 0 calls, we can have 1 call, and we might, we can have arbitrarily many calls. But let's say we cap it out at n. We stop caring after n. If I can guarantee that my information about this always goes right, then I can guarantee that I always terminate. If I count the number of calls I do, really. Which essentially amounts to simulating the program, but we'll cut ourselves off that for a certain amount of time. The point is that there are a bunch of questions that this might take the form of, and they might have a bunch of different answers. I only care that there are answers, and there's finitely many of them. Okay, I'm being very, very general here. I'll show you a specific example soon. Okay. Yeah. It doesn't necessarily need to be Boolean. You can have associated data. You just need to be monotonic in some sense. Yeah. So this can make our answers wrong. I'm going to show you an example. Yeah. The program is before the analysis. The analysis is running on the program when you pre-specify the program. Yeah. Yeah, I wouldn't worry too much about that. Yeah. Okay. Let's look at a specific example. So remember control flow graphs? I've got one for you. We start here, we go here, we might loop here, and then eventually we return Fs. Okay. And what we want to know is we're going to do a very classic data flow analysis on this called constant propagation or constantness analysis. I want to figure out which of these variables is a constant at the end of this function, okay? Here's how we do it. We just march through the CFG and we ascertain which of the program points, which of the, between each instruction, what thing is constant, okay? And I know that you can look at it with your eyes and then tell what the answer is, but let's do it programmatically right now so that I can convince you that it's possible to do, okay? So let's do it this way. I'm going to call it a loop invariant. That's not how I think of it. Tony Hoare actually invented the idea of like, or like he invented Tony Hoare, yeah.
Crazy.
Tony Hoare, yeah.
I didn't know this was funny.
Yeah,
Like,
Sir Charles William Tony Hoare to you.
is it really?
He's a sir, yeah. The Williams part is wrong. The Charles part is right. Okay, sir to you. Okay, stop. All right, we're gonna do the constants analysis.
Everyone knows about Hoare. I don't know.
When you start at the beginning of the program, we have no idea what is constant and what is not. But as soon as I see x gets 1, well, let me update my set. And this is a set, okay? I'm going to say that now my set is, I know that x is constant at 1. And I see y at 2, so I say, oh, now I know that x is constant at 1 and y is constant at 2. This should make sense to people. Like this is my advanced knowledge as I go through the program. When I land here, I'm just going to inherit my previous thing, right? So I still know that x is constant at 1 and y is constant at 2. But what happens here? Oh, well, x is constant at 1 and I add 2 to it. So now it should be constant at 3. Yeah. This won't change later at all. But hold on, I can't go here yet. I'm not done because I've got a loop here. I might go back to the same block. So what do I need to do? Well, what amounts to this is that I need to check all of my entry points. I need to consolidate this information. These sets here are kind of special. We call them out sets. These are kind of like the reported state of the world at the time that you leave this basic block. And we have two contradictory things happening here. The state of the world when I go from here to here is that I know that x is constant at 3. The state of the world when I go from here to here is that x is constant at 1. Does that sound to you like x is constant? I have 2 points I can enter with where now x could be 2 different values. So it's no longer valid for me to say that x is 1 or x is 3. Here's what I'm going to invent. I'm going to invent a symbol. It's going to look like a T. It's actually called top, but it means not constant. Okay. Basically what it means is that I need to follow this loop and re-enter here, but with that updated information. So with this information and this information, I'm going to conclude when I enter here, actually, x is this weird, funny symbol. X is not constant because I could enter at 1 or 3, which means that definitionally it's not constant. There's more than one definition reaching me here. Okay. And then I do the march again. If I feed a non-constant into +2, I get another non-constant, right? So this is now non-constant. And now I iterate that process again. Like, do I visit here and here? Well, non-constant and 1. Oh, that's not constant, right? So I get here again. Like it's okay. This is perfectly consistent with both of these again. My in state here is consistent with both of the out states that reach me. So I go through again and I'm done. Like I converge. I stopped being able to go up. And then I exit. I skipped a lot of coding details there. Like implementing this is quite more subtle. But this is the idea. It's simply that if you don't know this, you don't see this, but what this is a monotonic function. I'm saying that like we can only get certain amounts of information, and as we get more information, we eventually stop. When I get an information about it being constant, that's all well and good. That's cool. I say, hey, it's constant. But then when I get another bit of information, now it's not constant. Now I'm done. Not constant is the highest I can go. I can either know nothing. For a given variable x, I can either know nothing. I can know that it's constant at some number n, or I can know it's not constant. But I always go up or right. It's a monotonic function, but I happen to be doing it for every single variable, which is fine. Okay. Do people kind of spiritually get what I'm saying here? Thumbs up, thumbs down. Give me a temperature check. Confused, thumbs up. Confused, thumbs up. Okay, okay. Just want to make sure. This is a silly example. Okay, you guys looked at this immediately and you were like, yeah, we loop forever. X could get added to 2 by any number of times, right? But the really cool thing is that this method I'm describing to you, data flow analysis, works on any control flow graph. When these graphs get big enough that we can't possibly run this on ourselves, look at it with our own eyes, it's still going to give us the right answer. It's going to give us an approximation though. Like, so basically what I'm saying here is that the end result of this analysis is we conclude, oh, X is not constant, Y is constant. So when we return X, we know we can't, for compilers, this is important. We know we can't optimize this away, right? If X were to be constant, we would be able to optimize it and say any call to this function would always give back whatever X was. So if this was ret Y, different story, we'd be able to optimize. But because it's here, we know we can't, okay? But do people see a problem with that? Like, will this always do the right thing? Or our decision to optimize or not? Yeah. That's true, yeah. I was thinking more of the opposite end, actually. Yeah. So if immediately after this I put X gets X plus 2 and then X gets X minus 2, we'll be fine. Yeah, like here. Then we can do a little bit more advanced analysis, yes. But like for this program, basically what I'm trying to say is that our inclination that this is not constant was founded only upon the idea that, oh, we can go here. But this is a control flow graph. It offers a suggestion, a possibility, a probability space of paths we might take. This program might have a precondition on it where I literally never enter this loop. I always go here and then I immediately exit. In which case, yes, it would be constant at 2, or 1 rather, 3 actually, sorry, right? If I always go this way, I would always have an output of 3, right? But I don't know. I don't know without running the program. By looking at the control flow graph, I'm approximating. I'm saying, okay, assuming that you do exercise every single control flow path, then yes, we can conclude that X is non-constant. But it's an assumption. Okay, you know what they say about assumptions? It makes your program analysis sad. So we're not going to be able to do this in general. People get what I'm saying? Okay, so that's why this is strongly terminating, but sometimes it lies. Yeah. Yeah, there were 2 bits of information. X is 1, X is 3, and they were yelling at us, and they screamed, and then we were like, okay, I can't hear you. Not constant. X in both contexts was just a different constant. That's what mattered. And then here, when we enter, it's not constant. It's still true that on the outside of this block, X is 1. And on the outside of this block, well, eventually we updated that too. Yeah. The point is just simply that, like, similarly to polymorphism, actually, if I enforce too many constraints on X, if I say X plus 1 and then I say X string concat high, I get bad. Same thing here. I can only accept 2 bits of information. 1 to tell me if it's constant, 1 to tell me if it's wrong, or 2 constant, really. Okay. Yeah, we'll move on from this. I just wanted to give you a taste of this. Compilers really drills this into you. And yes, this is a prettified version of everything I just did. Okay. But this works for any control flow graph. And the reason why it works is that we're really moving up something called a lattice. Okay. And you don't even know what a lattice is, but it induces this pretty picture. But basically it means that, remember how I was annotating between every instruction with these sets? It turns out that we can only ever go up. If I start here, I can only ever go to this transitively. I can go up 2 at once, for instance. But I only ever can go up. And that means that eventually either I reach here or I converge somewhere below. Okay. So that's why we always terminate. It's because of this theory of lattices. Okay. Which is a really, really funny way to call it. And it's like, if you want to sound smart, it can be like, oh yes, this lattice has finite height. This is a lattice theory problem, but you know, whatever. I don't care. Okay. And it also induces really pretty pictures. That's pretty much all I wanted to show you here, is that the picture looks pretty. All right, cool. Okay. Okay, and this is kind of just justification for what I told you earlier. The point is just that, like, this is an information thing. Why can I only go up? It's because if I know nothing about a variable and I learn that it's constant, I can't go back to knowing nothing about the variable. If I have a variable and I know it's not constant, I can't go back to knowing that it's constant. So we're just structuring our information in a way where we can never go back. And because we can never go back, then we ensure that we always converge. Okay. This is the theory of data flow. And honestly, in program analysis, when I took it, we spent 4 weeks proving that it like terminated on various things, and I was not here for it. Oh yeah, here's a funny story. I literally got an R in program analysis at CMU. So maybe I should have opened up this lecture with that before I started talking about it. Because it was senior year and I was burned out and I just like didn't care anymore. And we spent 4 weeks proving that this terminated, and I was like, I'm now. But that's a fun thing I always get to say to my coworkers. Like, yeah, what's up? I'm a program analysis engineer. I failed program analysis at CMU. Like, yeah, I told my CEO that on the first day too. Cool. Okay. Right. I already said everything here basically. Okay. And then there's a few like analyses that are pretty cool that all fit in this framework. Okay. Data flow analysis is a framework. It doesn't need to solve just this question. There's other questions we might solve, like available expressions. Is there a definition of this expression already? That means like I can piggyback and use that. Do I need to redefine this expression? Like I can see, oh, I already did x plus y, like val z equals x plus y exists, so I don't need to recompute x plus y. Or we might do liveness analysis. Like I might look forward and say, does this variable have a use in the future? And if not, then I can use my IDE and warn you, hey, you don't use this variable. Or I might do something called taint tracking. And this is a really interesting one. Taint tracking is, does data from like a really sensitive call, like reading from input, go to eval? Y'all have taken 112, right? Have you ever tried doing eval of input, left paren, right paren? Has a 112 TA ever told you that's terrible, never do that again? Okay, it's incredibly unsafe, never do that again. The point is that taint tracking lets you find stuff like that. Okay, I'm gonna hurry along here because I don't actually care about the coding details here. Yeah. Yeah, what's up? No. You can do this in an imperative language too, and it becomes significantly harder in a functional language. Or sorry, in an imperative language. Yeah. Okay. Why the hell did I tell you about data flow analysis? Well, it's kind of because program analysis and people, we have one trick up our sleeves really, which is data flow. Okay, so I kind of have to tell you data flow, even though really it has nothing to do with functional programming. Okay, the implementation, I've done it. It's like it's okay. It's not worse for sure, but like there's nothing special about doing it in SML. Okay, but data flow analysis is interesting because remember, control flow graphs are at the level of abstract assembly. That means I got to break apart all my nice language constructs. I got to break apart every for loop, every x plus y plus z, and desugar it to its constituent commands. So I like to think it's a more imperative approach to program analysis because it's closer to the assembly. It's closer to what the program's really doing. What if I wanted to stay at the level of the AST? What if I wanted to stay where all the semantics were? We're going to see actually this is a really nice way to do things. Enter Semgrep. Okay. So here's the idea. I want to basically tell you why we should stay at the AST level, because why does it make sense to do program analysis on ASTs? ASTs are literally like farther left in the pipeline from the assembly, which is God's own truth, right? But the point is that actually there's a lot of reasons that are not strictly technical for why this is a good idea. And before I do that, I have to tell you about software engineering and security. These things do not go together, okay? In general, software engineers are paid to write code, and they're judged on the quality of the code, and they are judged on how fast they write it. They are not necessarily judged on whether or not they write secure code unless it comes back in the butt to bite them. So in the general case, people don't care about security, which is a great thing if any of you are aspiring to do security. Prepare to be ignored by developers for the rest of your life. But so generally security takes a backseat. Okay, why am I talking about this? Well, for a compiler, being wrong is a really fucking bad scenario. It's really hellish because we're screwed. For program analysis, it's Tuesday, okay? Being wrong is like, that's all right. What do you expect? Unsolvable problem, blah, 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 and then you just say that to your customers and they're like, okay, fine. Why to the developers who are getting security notifications, like they write code and then their GitHub yells at them like, oh, you have a vulnerability here. You'd better be right a good amount of the time, because otherwise, if you're wrong most of the time, whatever company or whatever place is using your tool is going to rip you out, and they're going to just not scan their code, I guess, or use a different one, right? So you can't be wrong too often. I'm saying that like you can be wrong, but like in practice, if you want to write a good program analysis tool, you can't be wrong all the time. So why am I mentioning this? Okay, my point is just that it's very, very easy to save labor if we stay at the language level. This is why I like what I do even though it's program analysis, because I'm a languages nerd. I love ASCs. I love recursive functions on trees. But it's really, really nice. Remember that we have a compiler that can turn from token list to an ASC, a tree. We can turn from a token list to a tree. If I want to write a program analysis tool for Python, I got to do this for Python code. I got to turn tokens into a Python ASC, and then I got to turn tokens into a C ASC if I have a program analysis tool for C. There's an immense amount of duplicated work here. I can do this for C, I can do it for Python, and all the while I have different ASTs for C, I have different ASCs for Python. I redo my analysis all the time. So why am I duplicating my efforts here? Almost. Yeah. This is what the pipeline looks like. This makes me sad. Do you see how many purple and blue nodes there are here? That's bad. Let's do better. What if we had, so all these, to be clear, like if I did this in like SML, all of these ASCs would be different types. We'd have like data type Java underscore ASC, we'd have data type Python underscore ASC, and it just becomes a massive pain in the ass, okay? Like when Java upgrades to Java 21, you're gonna have to change that. When Python adds match statements again, you're gonna have to do that. Like, come on. So what we can do, before I say that, most programming languages, so, okay, I know I love complaining about programming languages to you, but it's mostly for comedic effect. Most programming languages look pretty similar. A lot of them have for loops, a lot of them have while loops, most of them have variable definitions, most of them have functions, okay? So why should I necessarily represent them differently? They have different idiosyncrasies, right? Like Java does class inheritance and Python does blah, 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 blah. But also, we're solving an unsolvable problem. So what if we just took all of those like minuscule differences between languages and we just like shoved it under the rug and we just were like, unsolvable problem, it's fine. For program analysis tools, being wrong is Tuesday. So what Semgrep does is Semgrep just parses every single language to the same type. It represents every single language, programming language, every program the same way. And turns out this is actually really, really cool. And it's why we support over 24 languages, because it takes you like 3 days to add a new language. It's like not a big deal. And this is why. Here's the pipeline. I take Java code or Python code or C code. I turn it to this type that I call the generic AST. And then moreover, I don't have to do parsing I don't have to do analysis multiple times. I just run an analysis on the AST. This is actually a really cool idea. No one, I don't know if anyone else says this. I work there. Okay. So you have to be pragmatic when you're solving an impossible problem. Let's move on. Okay. So here's some Python for you. Thank you. Here's some Python for you. Who reads Python? Do we have a 112T in the room? There's a 112T in the room, right? There's a 112T. Who's the 112T in the room? You are? Okay. What's wrong? What's wrong? What's wrong? What's wrong?
The list is mutable.
Cry about it. Cry about it. Cry about it. Okay. Mutability. Right? What happens here is that you might think this is going to be default nil every single time, but it's not. But it's also not called nil. Here's what happens when you call append 2 of 2. You get the list of 2. Cool. Sounds good. But you call append 2 of 2 for the second time, you get 2 comma 2. Why? Because this guy is instantiated once the function is, and then it's mutable. So every time you append, you change this guy, and in the background, it's kept. This is a very common thing that people might do. Okay, like this is stupid, but like when you look at it with your human eyes, bless your heart, like you can see this and be like, that's garbage. We're talking about Python here. Do you expect something better? Bless his heart, Guido Van Rossum, bless his heart. I love you, Guido. Okay. The point being that with your human eyes, you know this is wrong. But who's got time? Remember all the tens of millions of software developers out there producing garbage code? Do you have time to go look at all their code? No, that's what I thought. Okay, you have better things to do, like read memes on Funny Me or whatever. Okay, so my point is that this is bad. Let's see if we can catch it in an automated way. Let's see if we can fix such bugs. And oh, the other thing I want to say about it is that we don't need to go to assembly to know that this is a problem. In fact, we only see this because we're above assembly, right? At the language level, this is a bug. And most bugs are at the language level, at the level of your source text. Why? Because developers write source code. I don't often write assembly, okay? I did for 213 for a bit. Okay, so the point is just that let's not go further down. Let's stay at the AST, okay? All right. So program analysis can do a lot of things. I gave you a few examples earlier. One such thing is security. I want to find if there's a vulnerability in my code. Another thing is stuff like what I just saw, best practices. I want to make sure you don't do dumb things like do dumb Python things like default immutable arguments. Okay. But it all just comes down to finding things that you're interested in, which I will call a finding. Okay. What we're going to do with Semgrep is we're going to try and customize, and I'm showing you this because you can understand what I'm doing, basically. Okay. You are all capable of understanding what I do at work. Semgrep basically will be customized to all of these. Some things find security vulnerabilities. Some things find style errors. With Semgrep, you can find whatever you like because you're going to be able to specify it to Semgrep. How do we do this? So, has anyone used grep? Has anyone used Control F? Congrats, you've used grep. All right. So grep is basically just Control F. Okay. And the point is just that if I wanted to find all instances of a call to a function print, if I Control F for print in my VS Code extension IDE, what do you think is going to happen? It's going to highlight every single call to print, every single print, including print all or printing, so on and so forth. Okay. Or if for some reason I had a variable named printing underscore press, okay, it would find that. Okay. The point is, whatever. The point, no, that's still fragile though, because what if there's a new line? What if there's anything else, right? So the point is, we're going to be inundated with results. We're going to find every literal instance of this string. This is literally just looking at sequences of characters. That's super dumb. That's super, super dumb. Let's do better. How can we do better? Well, Semgrep can understand the semantics of the program. We're going to look at the AST. Remember that midterm 1 problem I gave you, or midterm 2-1 problem I gave you about tree matching? Well, Semgrep doesn't do text search. What it does is tree search. I'm going to try and, given an abstract syntax tree like valdec, and maybe we're declaring x, and we're declaring x to be 1 minus 2. Okay. I want to find a subtree of this that matches my pattern. Okay. And here's how we're going to do it. We're going to have two ASTs, a pattern AST, which means the thing we want to match, and the target AST, which is the things we want to produce matches in. And I'm going to give you very concrete, pretty pictures. And this is actually so basically you would give Semgrep this, okay, for the next few slides. This is what you'd give to Semgrep. This is what the program that you're analyzing is. And these are the ASTs as I have prettified them, okay? If I wanted to find, say, print, know that there's this let's print here. If I wanted to match this print on the AST level, there's only one choice, right? This guy. Any subtree of the right tree that matches this, but not this. Why? Because it's not the same color. It's not the same. This is a string that's a print call. Different things entirely. So what will happen is that it'll be like, yeah, cool. And it'll highlight it. I very briefly toyed with the idea of adding SML to Semgrep. It would take me like 3 days. It wouldn't be hard for the purpose of this demo. And then I realized that I do not have 3 days. So I didn't. But one fun thing is that Semgrep actually works with OCaml, which is basically the same thing. So if I had this on the right-hand side, basically I'm showing you that this is the thing that we're specifying to Semgrep we want to find. If I click play, it'll highlight this, but not this. Okay. This is just me justifying to you that I'm not lying about what I'm showing you on the slides. Okay. It's better than regex. Yes. It would be actually, I'll show you a really cool example here. Okay. I don't care about this. Yes. Okay. But the algorithm is very, very simple. It's very understandable, right? You just go and find the node that matches. I think that's a really cool thing. Okay. It's a kind of an idea in functional programming, like simple, like beautiful fundamentals leads to good practice. This is the fundamentals. Okay. What if I wanted to find calls to ref? Remember the thing where I told you, one of the good things about in SML is that you're very explicit about where you use mutability. Everywhere you say ref, that is a call to a mutable thing. But we don't want to control F for the same reasons I gave you earlier. This is what's called a meta variable. It means match literally anything here, any kind of like AST node, any expression. Okay. So the tree looks like this. It's a function call from ref to this meta variable, which is like kind of grayed out because I don't know what it wants to match in. Where's the match here? Is there a match here? There's going to be a match here because why? This is the same as that. This is the same as that, even though I made the colors different for some reason. And then this can match the meta variable because the meta variable matches anything. Okay. The meta variable is a standard. It's just in the same way that you say val x equals e, right? It matches to whatever. And I can show this to you also. Oh, maybe I should just not do that. Okay, whatever. Right? But I'm still not going to. And if you see let, that's val. Like, congrats. Now you know OCaml. You're welcome. Okay. But if I did this, it wouldn't happen. If I did this, it wouldn't happen. It's open source. This is all open source. You can go see the code that I write. Actually, please don't look at the code I write. No, I wouldn't feel right about talking about this if it wasn't. I wouldn't feel right about working at Semgrep if it wasn't open source. Like that's just personally me. I'm very grateful that in my lifetime I've been able to work on majority open source projects. I like them. But anyways, yes, this is open source. You can just run this, and we find the finding, and it's doing it via tree matching, which is a fundamental thing that you learned, right? What if I wanted to soup it up a bit? Okay. What if I wanted to use a meta variable 2 times? If I do this in SML, okay, I probably committed a stupid here, right? Because like this is always going to be true. So what I'm trying to say is that if I have the equals operator applied to 2 of the same thing, probably something weird is happening here. Meta variables can unify when you use them multiple times, meaning that whatever they match has to match each other too. So if I produce a match here, right, equals matches here, and these meta variables match these, and because these subtrees are the same, they also match. Yeah. But the great thing about program analysis is that you can do this if this were C, we would still be able to do this, and we have options that let you configure it because we can be wrong. We're allowed to be wrong. If you do this, it's still kind of a code smell. Like if I do, what's on this board? Let's run. Oh no, it's not something I liked. In an imperative language, any language, if I wanted to do like f equals f, like regardless of if it's imperative, like something is weird about this code. Okay, so you can configure whether or not you want to find that kind of thing. But yeah, that's why I love program analysis. You can just be wrong. I can just write code and be like, yeah, like I know this isn't always right, but like in practice, it should be right. And then my manager's like, yeah, okay, fair enough. It's Tuesday. It's Tuesday. It's Thursday. But in this case, if I said f2 equals g2, I didn't update this either. I'm sorry. This would not produce a match because if this were g, these would be different trees. Thumbs up, thumbs down, thumbs sideways. You're following me here? We're just doing tree matching. Okay, cool. All right. Oh, I don't know if I have any. Yeah, it's pretty much just pattern matching with extra steps. Again, clean principles lead to good code, right? The guy who thought of this, one of the guys on my team, Johan Padulo, he's a PhD in program analysis, and he's like super good engineer. But this was his invention, and it's like literally the best thing ever. Yeah. Okay. But okay, I've given you some pretty abstract examples. Let me show you something concrete. Remember that part where I was like, do not do this. Usually this is a code smell. Why? Why? Yeah. Linear and L. And if you're doing this recursively, you're probably, cruising for a linear quadratic cost. Okay. So we don't generally like this. Hey, wait. It's very, very easy to write a separate pattern for this. These are 2 meta variables. I'm saying any expression appended to a list containing any expression. And the trees just look like this, right? Does everyone understand why this tree should be this? So append here, my left argument is E1, my right argument is a singleton list of E2. And then if I had rev, the tree is too big to represent, but like the point is that this would be the subtree here. And we could go ahead and match it. And I'm going to show you more OCaml, very, very exciting. Okay, what's going to do here? This is rev in OCaml. Squint your eyes, it'll look like SML to you. Okay, and if anyone has a fundamental like complaint with OCaml, I don't know what to say. Okay, but okay, $E1 append list of $E2, and it matches. But it wouldn't happen if it was like, say that there's like an L2 out here. That wouldn't happen because it's not a list. It's not a singleton list, right? So we can find very cool stylistic things like, and I know that I'm just talking about this and I like to talk about it because it's what I do for work and it's super cool. But this really is a labor saving device because this is so easy to write. It's literally a one-liner. Yeah. This append of X cons no. Oh, it would still be able to. Yeah, because we desugar those when we go to the AST. Yeah. Yeah, good question though. Okay. And this, because of this thing that all programs parse to the same type, we only need one matching function. We take in an expression on the left, an expression on the right, and we give back what's called findings. But it can happen for Java, for C, for OCaml, for Python. It doesn't matter because they're all the same type. Okay. I don't have to duplicate my analysis per language, which is a really, really cool thing. So remember that default argument Python thing? So this one is good. This one's bad. This one is also bad. This is like Semgrep syntax. I don't need to explain it to you. You're not going to use Semgrep, but I just want to talk about it because it's cool. We're going to find these because we have a default instantiation to this list. Yeah, that's all it is. That's all it is. And the real cool thing is that it looks like code here. You don't need to have. That's kind of the other thing, which is like program analysis. We're playing a game where like I talk to you a lot about ASTs and control flow graphs. And the average developer, guess how much they know about ASTs and control flow graphs? The answer is frighteningly little. Okay. So the fact that you don't have to know anything about ASTs to write this is pretty cool. Like the tree matching is happening, but it's happening behind the scenes. Like you just write, oh, magic $D equals nil. And then it's like, okay, sounds good, boss. Yeah. This one would only parse as Python, but I could definitely do something like, what's another language like I vaguely know? Thai, let's just say int main int x c. And if I remember my syntax, yeah, here we go. What I've done is I've converted this into a rule that just finds C functions that have a argument that's an int. So if people read C, I just like context switch to C here. Yeah, you can write certain things like $x plus $y, and this will parse in like C or Python, right? This is usually rules are one language. It doesn't really matter. Yeah. Okay. Oh yeah, the next things I want to show you is this taint tracking thing. The thing I was talking about eval of input, yeah, it's pretty bad. Don't do that, by the way. But if you were to do that, program analysis tools can occasionally have your back because we can write this. This is a taint mode rule. It's just saying that like input is bad, and if input goes to eval, that produces a bad. And here, eval goes to input, or input goes to eval. Yeah. Race conditions are hard. Very hard. Because the things you have to specify what you're looking for. How do you specify like what a race condition should look like? You know, it's very hard. It's very hard to diagnose these things. Almost, if you're writing concurrent code and you have a race condition, usually it means that you're writing mutable concurrent code. And remember what I said about how if any of you write mutable concurrent code and then come back to complain at me 5 years later, I'm going to send you back an angry face, and then I'm going to. No, okay, never mind. I was gonna make a joke, but it would not be good for me to say that. Yeah. We do the same control flow graph thing. Yeah, there's actually both the AST analysis, and then we also desugar it to an abstract assembly, an IL. Something like that. Well, not quite. Like if you did stuff in between, it would also know about that. Like pass x equals 3, or actually no, not x equals. Actually, that's a cool example. Let me show you this. Here. Oh, wait, what happened? Oh, it's because I shadowed the name. Sorry, my bad. Okay, y equals 3. We still get it. X equals 2. What about this? We no longer get it because x is now no longer input, right? We killed the definition that was passed into me. Yeah, I don't know. Constant propagation. I just want to show this. I'm just gonna keep showing you stuff because I just want to put a lot of work into this. Okay. Foo of 2. If x equals 2, then this is gonna be a finding. If I say x equals 2 and then y equals x, foo of y is also 2. It understands that. If I say x is 1 is y is x plus 1, then foo of y is still 2. Otherwise, foo of 1 is not 2. So where? Below the foo of 1. Probably this would not work, I would imagine. Yeah. Wow. Yeah. You can run into weird things with like names. Like names are kind of hard. Like it's kind of hard to like look at x in 2 different places in a program and tell if they're the same x. But we do it, by Jove. We try. But it means that basically like this kind of example I just showed you is semantics aware, right? Your analysis should be aware of the flow of code. When you say x equals 1 and y equals x plus 1, yeah, it's 2. That's what it does. And I'm glossing over this, but this is a lot of concentrated work by like a team of like 8 people for like 2 years. Okay, so like, I love you, Ago. You're doing good. All right. Okay. Yeah. Okay. Wow. Bells and whistles and analyses and looping forever, and we are almost at the end. And I didn't think that I would actually make it to the end, but I guess I sped through some things because I felt like it. What is the point of this lecture? Why did I give this? Well, it's not because it's an ad, because like, and I know that I'm suspicious of this kind of thing too, but like, what I started off, I came in hot with this idea, this quest, right? We are solving an unsolvable problem. I truly, duly like believe in this idea. Like there is a large mountain of code that's slamming into us at like breakneck pace, and we got to do something about it. Because go read that book I linked. Like it's a really good book actually. It is terrifying. It's terrifying how much code is being written, and especially by how much code is being written without any care or consideration. One thing that people always like kind of, I think to myself is like, functional programming. I feel very strongly about functional programming. Shouldn't my goal be to go out and make everyone else do functional programming? I'm a realist. I'm not going to do that. Okay. Like I can't make people do that. Like there's applications where functional programming is used. There's applications where it's useful. I'm perfectly fine with that. But I like to think about it in the sense of like making an impact, which is like what I care about, like the three things I care about. And this is going to develop into a philosophy thing, but like I care about three things. I care about solving interesting problems. I care about doing it via principled means. For me, that means functional programming. And I care about making a real impact. And this is something I like struggled with a lot, like my senior year, when I was thinking, do I want to go to do a PhD or not? And I figured that it wasn't for me. I didn't enjoy doing the research. And I've been thinking about this for a while. And I think like to make a real impact. And I think this is something that all of you should be thinking about, because you're coming out here with this education. You're coming out of here like with hopefully your degrees. From CMU, and you're going to go out and do really, really cool things. And only when I got out of CMU did I realize, like, actually, when people tell you you have the potential to do blah, you can do whatever. Like, yeah. Only once I got out into the world and was like, oh, wait, hold on, I'm like mildly competent. I didn't expect that, right? And you're going to be hopefully better than mildly competent. So when thinking about impact, basically, there's two ways I want to think about it, right? There's two ways I like to think about it, which is in terms of numerators and denominators, in terms of like n over d, right? Now, to make this number bigger, to make the impact you have bigger, right? You could look at it as, I want to be a very big numerator. I want to be Jeffrey Hinton. I want to be, I want to be this like big person that does everything. I want to be Po Shen Low. Okay, there's a way you can perceive that, and you can look at it that way. But there's another way you can make a big impact. There's another way you can make a real difference, and that's not by making the numerator bigger, but hey, math fact, making the denominator smaller. When I say make the denominator smaller, I mean this kind of idea of doing widely ranging things, do things with breadth, affect everyone. When I'm going here to find a meaningful problem, one of the most meaningful problems I think I could pick in the world that fits me perfectly is program analysis, because I get to affect every piece of software ever written, every piece of software that's currently being written, all of the software that people are writing that is terrible and horrible. I don't have to convince them to use functional programming, because I still feel good about the fact that at the end of the day, what I'm doing, this program analysis stuff, is in my favorite language, OCaml, and it's done functionally, and it's principled, and it's all the better for it. So I guess I just wanted to bring this back to the fact that, like, for me, I think there's nothing cooler in the world than program analysis. I think it's the perfect application, and I think it has real world impact. And I think that all of you can have a real world impact too. Just like find the problem that interests you and find a way to do one of these two things. Either is fine. And it's okay not to care about impacts, but I think that we're tackling a really important problem. And our motto, our mission, is to profoundly improve software security. And I'm really glad that, like, not only do I have the chance to come here and teach, but I've been able to do that at my work. That's it. Thank you.